show, though. I have to try that, though, in my classes. We're talking about, you know, the modeling of the power grid, and if you look at how it can be broken down, on the generator side, there's a machine model, and that's what Jamie talked about, and he left us with a field voltage. And the field voltage is what drives the machine, and the exciter is what controls that field voltage, and it's taking sensing coming in from the grid in a set point, and it's controlling the field voltage ultimately. So we're going to talk about the exciters. The exciters have an input from the stabilizers, which we'll talk about probably tomorrow. And then we're going to talk about the part of the grid or the generator model that controls the speed on the machine, which is the governor. So we'll talk about governor models as well. This is from a grad class that I teach. Jamie talked about the machines. Usually we don't talk too much longer about machines than he talked about, but usually governors and exciters, we probably take maybe 4 75-minute classes on it. So this is condensed down a little bit, but you know, ask questions throughout. This is a different way of looking at how information is flowing within the simulation. You've got the machine model, which is interacting through the network or with the network, and Jamie talked about that. The exciter is putting out a EFD, and it's getting potentially a voltage from the machine model. It's getting a reference point coming in here and potentially a stabilizer input. Then the governor is going to be putting a P mechanical into the machine model, and then it's going to be taking back electrical value that it uses to get the speed on the system. With the wind turbines, the stabilizer plays a different role. It's not really a stabilizer, but it's what we use in place of a stabilizer with the wind models.
What's the LCSD?
That's a model that can change the set point on the governor. We're not going to really talk about that today. That would be in the longer presentation.
Stands for load control frequency bias.
Okay.
Just looking at the system frequency and maybe changing it.
All right.
So mostly we're going to look at little examples here, and some of this will be hands-on. But if one loaded up a WECC model in the add-ons, you can go to stability case info, and it says models in use. That gives a summary of all the models in use. And if you look at the models in use, I've got it cited or sorted by the model class here. These are all the different exciters that are represented in a WECC case, all the different types. So there's probably about 45 of them. And then on the governors, there's, you know, maybe 20 different governors that are used. So when you're running a run and you hit the run button, there's a lot of different things going on in that. And a lot of these things can cause problems. So you kind of want to know what's going on with them. So we'll talk about that some. One of the nice things in Simulator is if you go on this display and say you want to get information on, let's just pick the, we'll do the EXSTI_GE model. If you click on that line and right click on it and do show dialog, it shows you all of the exciters in the case with that model type. Each model type has particular parameters associated with it. This lists out all the parameters associated with all the different exciters of that type in the case. So you can kind of get a feel for what's there. Is it good? Is it bad? Things like that. You know, Power World lets you, if you click on the top, it'll do a sort, so you can kind of sort and you get metrics on the columns and get a feel for whether data is good or bad. Sometimes when we're doing a run and we see a problem popping up, we might look at the model and compare its parameters to others of that same type. And if the parameters look out of whack, there might be some data entry errors there.
Or we might just gene at the generator and do that.
Well, yeah, I mean, sometimes you just take the generator out, you just get rid of the model. Yeah, I mean, sometimes you turn it off, but it gives you a feel for, is there outlier information here that might indicate bad data?
Do you have your metrics available for display on below the header? Like, you know, within a range or function of some other variable?
Alright, are you saying, here's a TC parameter, what's good data there?
Yeah, like if there was a way to display whatever you're checking internally to valid or, you know,
We don't
do
show,
a sanity check.
Some of
We-
them with the WECC data check thing will pick some of those up.
yeah, we do some, when we validate a case, we do some checking on it.
But
If-
very little.
Yeah.
Not very much.
I mean, if I wanted to look and say, here's this KA value, what is it doing? I might take that column and sort it, and then plot the sorted values. And then I would pick a better color.
Yellow.
Yeah, yellow's a good one. You know, and there you can look at KA's range. I mean, you know, it's kind of varying like that. Then there's a couple where it's really high. If I was having trouble and it was associated with a generator that had, or the exciter that had a gain of 3,000, I might suspect that gain. 3,000 seems like a pretty high gain there. So-
It's really hard. I mean, the nice thing in PowerFlow is if somebody puts in a limit of 10,000 millivolts, every engineer knows that means we have no idea what the limit is. But the gains that Tom's gonna talk about, there really isn't that kind of intuition. It's harder.
Yeah, so I mean, we're trying to help you out. We're trying to make power system analysis and design as simple as possible, but that's not saying it's going to be simple. Exciters, including the automatic voltage regulation, the useful standards, IEEE standard 421.5, that's where we go to get new models sometimes. That's an update from the 2005 edition. But there have been papers on exciters going back to 1968. Kundar's book is another good reference on exciters. This is the basic black diagram for an exciter, which I got out of Kundar's book. So there's the machine model, which Jamie talked about. There's the exciter. It's got a voltage regulator that's taking some reference point in there. It's sensing something, and it's got potentially an input from a power system stabilizer, and it's got potentially limiter inputs coming into it as well. Jamie talked about the overexcitation limiters and the underexcitation limiters. They're going to play into the exciter, and we'll see that as we go through the model development. When you look at exciters, there's different types of exciters. You could certainly have a generator with no exciter. You could have a permanent magnet machine. That would primarily be used with a wind turbine where you've got some other sort of control, because of course if you have a permanent magnet, you don't have much control on it. You can have a DC machine exciter, those are the older ones, an AC machine exciter, or a static exciter. And we'll talk about each of these classes without delving into too much detail, given the time here. How many folks are pretty familiar with block diagrams? Okay, so some of you are, some of you aren't. I'll go through block diagrams, but when we talk about models in power system dynamics, usually we express them in terms of block diagrams. And this is a very common exciter. It's an older exciter, it's the IEEET1. It was standardized in a paper from 1968, represents an exciter based on a DC generator. So I'll go through on the next few slides and tell you what these different blocks mean on it. But in all the exciters, you're going to have an output, which is a EFD, which is going into the machine model. So ultimately, this exciter is saying, what is the field voltage going into the DC winding on the machine? And then exciters will have some sort of input, which is either the voltage at their terminal VT, or more likely it's a compensated value somehow. It's sensing something from the system, the voltage in the system of what it's trying to control, and then it's got a reference point here, where do you want it to be, and then potentially other signals. And we'll go through this in a little bit more detail in just a second before I go through first I want to go through the block diagrams. So I'm going to go through and kind of make sense of the block diagrams here that will be used throughout. To simulate a model represented as a block diagram, the equations need to be represented as a set of first order differential equations. So we love seeing block diagrams because having done this now for quite a few years, we know how to take a block diagram and represent with differential equations and code it up. Okay, so what are some basic block diagrams? Probably the simplest one is an integrator block. The S is the Lagrange operator. This says if you have an input, you multiply it by some gain Ki. 1 over S is just saying you integrate it, and then you get an output value. So that's just an integrator block, and you'd represent it with differential equations given like that. Whenever we deal with block diagrams, we have to initialize them because they're ultimately getting initialized from a power flow. Nice thing about an integrator block is if you know the output in steady state, the input to an integrator is going to have to be what?
0.
Yeah, it's going to have to be 0, otherwise it's not in steady state. So what we would do in integrating the code is we know the output, then we say the input's going to be equal to 0 to initialize to steady state. Another simple one is a first order lag. First order lag is just representing an output where the input might be a unit step, and then it's a first order differential equation where you got some lag going on associated with it. The two key values are the gain and the time constant there, TS. This is the differential equation associated with it. In steady state with an initial output of Y0, the initial steady state, the initial state is Y0 for the state variable, and the initial input is going to be that value, Y0 over K. These are commonly used to represent a measurement delay or some sort of delay function. This is a derivative block. It takes an input and differentiates it. And KD is the gain on that differentiation. We can never physically take the derivative without some type of time lag. So this TD just represents the time lag associated with that differentiation. In steady state, the output of any derivative, of course, is derivatives tell how things change. So if you're in steady state, it's not changing, so its output would be equal to 0. This is a lead lag block, which can be used for compensation. You've got a TA value, a TB value. In steady state, the S goes to 0. So in steady state, the input and the output are going to be equal on a lead lag. Okay, this is a little bit trickier to represent in code, but if you're interested, that's kind of how you represent it in the code. a thing that can be a bit of a issue in coding stuff up is to deal with limits. And with limits, there are two types. There's wind-up limits and there's non-wind-up limits. And when there's an integration, how the limits are enforced can have a major impact on the simulation results. A wind-up limit for an integrator block would be shown like that in a block diagram. What a wind-up limit means is that when you've got an input U coming in, you're integrating it, V can get as big or as small as you want, there's no limit on V. A wind-up limit just limits the output. And where that makes a difference is it makes a difference in how quickly you back off a limit. If you're integrating some input and V is very large, the output might be limited by L max. When U goes negative, the output is not going to change for quite a while. And usually we don't have physically too many of these. Usually we're going to be doing a non-wind-up limit. But if you have one like that, it's represented as a wind-up limit, and it can take a long time to back off the limit. Okay, this is a limit on the first order lag, and it would be coded the same sort of way. Again, the value of V is not limited, so the value can wind up. That is, it can go well above its limit, and that delay is backing off of it. This is a non-wind-up limit on a first order lag. That's the code in integrating it out. The nice thing about these is they don't wind up, so they back off right away. Okay, one issue that needs to be considered when coding transient stability is there can be ignored states. And when a block has a time constant equal to 0, that state is ignored. That means this is, in essence, infinitely fast, so we would just say U times K is equal to the output. So then it becomes an algebraic constraint. There's no differential equation there, and we just ignore it. With lead lag blocks, it's quite common to have TA equal TB, and if you go back to a lead lag here, if TA is equal to TB, they just cancel and it looks like 1, and it doesn't have any input. I mean, any impact is just ignored. Okay, so I have to deal with that. So if we go to this one here, you can see that there's a first order lag right here. This is the actual terminal voltage. That TR value is just saying, hey, there may be some delay in sensing that terminal voltage. TR represents the sensing delay. A lot of times it's set equal to 0, so then we ignore it and we say, hey, the measurement delay is so small that we don't worry about it. Here's a KA over 1 plus STA. This just represents the gain function here with a lag of TA. Here the output, you can see the output of that has wind-up limits on it between VR max and VR min. This is a feedback loop that is just a derivative feedback. So you can see the derivative feedback here. This will represent the dynamics of the DC machine, which we're going to talk to in just a second. This is just a voltage amplifier. Voltage amplifier has some gain on it, it's got some limits on it, and it's got potentially some time delay associated with it. Okay. I'm not going to review too much on the DC machines. DC machine exciters are not that common anymore. They're not particularly fast exciters, so they're not that common. But a DC machine exciter was just an exciter which is putting out a field voltage that was based upon a DC machine. I mean, keep in mind the challenge we have on a synchronous machine is we need to get a DC voltage and current into a spinning rotor. So there needs to be a way to get that voltage and current in there and to control it. So on that spinning shaft you can have a DC machine, and that DC machine is there just to put out the DC current. So on the stator, a DC machine has either a permanent magnet or a single concentrated winding. The rotor currents are then supplied through brushes or commutators. These are the equations for the DC machine. If you have kids and they have toys, maybe they've changed since when I was a kid or my kids were kids, but the nice thing about a DC motor is you had easy control of the speed because you varied the voltage and you changed the speed. You know, it's like when I was a kid I had race cars and I had a model railroad, and the model railroad you crank up the transformer and your train would go faster. You just put a higher voltage on there and your machine would go faster. And that's represented in the equations for the DC machine right there, which we would teach at the university in a junior level class. So there's different types of DC machines. You may or may not have a field winding. Usually we're going to have a field winding. In a toy, the field winding might be a permanent magnet. If you have a field winding, then you can connect it either as separately excited, where the field and the armature windings are connected to separate power sources. You can have it series excited, or you can have it shunt excited. And these values come through in the parameters that we get on the DC exciter models. So this slide here talks about separately excited DC machines. So you can see you've got two separate sources there. This goes through how the parameters in those equations get transformed into what we see in an exciter model. And I'm not going to dive into the details of this, but they'll pop out at the end. Just like we ran into with the machine models, saturation plays a role in an exciter because your exciter, being a DC machine, can saturate, so you have to account for saturation. So you'll see a saturation function there. And this continues the derivation through, this here is the equation that we ultimately are going to represent in the block diagram. The same model can be used for both by just modifying the value of K that appears in this equation here. So this K value is going to be different depending upon whether it's a self or separately excited exciter. If we look at some values in the WCC case, I think I got this from the WCC case. If you look at the KE values, some are close to 0 and some are close to 1. KE equal to 1 indicates it's a separately excited machine, and KE close to 0 means it's a self-excited machine. So we can represent them with both. So that's where the KE value is coming in right there. Okay. Just as Jamie talked about on the machines, we use a function to represent saturation. Just as Jamie talked about on the machine, there's two common ones that are used. It's either the quadratic approach or it's a scaled quadratic approach. Power World supports both of those. Sometimes you'll see an exponential function, but that's much less common for the saturation. This is the voltage regulator model. It's pretty much just a model for an amplifier. We've got some gain on our amplifier. Ka is the gain here. And then we've got some time constant associated with the amplifier. And then we've got some limits associated with the output of the amplifier. And that's going to be the control that we'll go through an example in just a second that we play with. And then on an amplifier, you can look and say what should be the steady state value on it. And the steady state value will be the reference value minus the terminal value. That's the input voltage to the amplifier. And that's going to be VR over Ka. Okay. The last part on this is just the feedback. In control systems, you often get instabilities, and one way to minimize those instabilities is to do feedback control. In exciter, feedback control is typically done using a stabilizing transformer with the values given there. When you work through the equations here, this just turns out to be the equation that we saw in the block diagrams, which is just a differentiation of the feedback signal. So if we look at the block diagram, the original IEEET1 exciter is given right there. It's got a terminal voltage that we're trying to control here. It's got a lead lag block, or just a lag block, that is the measurement delay. We compare that to a reference signal, subtract that off, that goes in, and then it's an input to our amplifier. Our amplifier takes Ka with potentially some delay there, we limit it, then this becomes a representation of the DC machine. And whether it's separately excited or not just impacts the Ke value here. And then that provides our field output. To get stabilizing, we use that stabilizing transformer, and it provides a feedback path right here that comes in there. In steady state, this is just a derivative block, so in steady state the output of that's going to be equal to 0. Now, I showed you all the different exciter models that are used in the WECC case. They're not all different. They're families of exciters, and one merges into another one. So this model was standardized in 1968. Go forward 13 years, and we get this one here that actually should look very familiar. What makes it look a little different is this block here and this block here are actually identical, even though they're represented a little bit differently. So this here is the same as that. On the amplifier, by 1981, people realized that we really need to use a non-wind-up limit. That's how the device actually operates, so they represented it with a non-wind-up limit, which is a better way to represent it. Here's the feedback path. There was a lead lag block added to allow some phase compensation if desired. Now we've got just the V error here, which may or may not represent a block there. And then this signal here would be this is a signal that gives a set point signal for it. Okay, if we continue on, the IEEEX1, this is from 1979, and is the EXSTI with the potential for a measurement delay and inputs for under and over excitation limiters. So in the IEEEX1, this here is the same that's the same, that's the same, that's the same. Here's the VS, that's explicitly a stabilizer input. Now, in this model, they're saying, hey, maybe we'll have an under excitation limiter or an over excitation limiter. Those guys just put signals into this summation here. And now we change VT to be EC. EC is just saying, hey, the voltage you send in there might be a compensated signal, which we'll talk about in a little bit. If we continue the evolution, in 1992, IEEE started producing standards. So the first draft of the 421.5 standard came out in 92. It slightly modified the EXDC1, calling it the DC1A, which is usually modeled as an ESDC1A. And it's like you look at that and you say, what are the differences? It's like tracing genealogies of these models. You know, it's like this here is mostly the same. This they just separated them out for whatever reason, but this is exactly the same. There's the amplifier, exactly the same. The feedback path is exactly the same. Now people said, hey, this under excitation limiter, it could feed in either on this side of the lead lag or on that side of the lead lag. And then you have a high value gate which just says pass the high signal.
And they got rid of the time delay again. Can't see
Yeah, they get rid of the time delay, and then it comes back, and then it goes away. But as we implement these in Power World, we just, you know, it's like, okay, I've seen this one before, so we just kind of drive one from the other, and you try to make sure you get everything right on it. So if you jump ahead to the IEEE, the standard 421.5 in 2016, what are we calling this?
They're all done in Power World. This would be the DC1C.
You read that from the bottom?
No.
Or did you
I'm
just know that?
Yeah, no, there it is.
Yeah, this is the DC1C model.
And we since we were able to put them in first, we just, wow, we took the name from the standard and we used it. Why doesn't everybody else use it?
Yeah, so now, I mean, you can just look at that and see it's like, okay, this is all the same, except now we've got a minimum on the EFD. There's a potential to put a lower limit on the EFD there. There's the amplifier. Now we've got the potential for the overexcitation signal to come in here or come in there. There's a potential for it to come in, for the underexcitation to come in here or come in there. Same feedback there. I don't know what that is, VSCL sum.
Stator current limiter.
Stator current limiter sum. Then you've still got your reference point, you've got the stabilizer input and the compensated value, which is now called VC rather than, you know, what it was before.
Yeah, Tom, those symbols are the labeled HV and HV gate, LV gate, those are.
High value and low value gate.
Maximum select, minimum select?
Yeah.
This.
This just says
Either a max or a min.
take the low value.
Oh, take the
You've
low.
got two inputs coming in, pick the low one. Actually, I guess you got three inputs coming in. This one says take the high value coming in. Yeah, so that's a high value gate and the low value gate. Just high value gates take the high value coming in, low value gates take the low value coming in. Okay. All right, I guess I say what it is.
Yeah,
Stator
and
current
all
limiter.
of those new exciter models are in Simulator, and no one has ever used any of them. They're all on there.
So in Simulator, let's open up the case. It's B4 gen RU underscore sat underscore IEEET1.
What was that again, Tom?
I'll read it when I open it's the only B4 one in the directory. So if you go open cases and you go to talk for, I'm sorry, it's not the only B4 one, it's the only B4 underscore gen ROU one in there. So in this directory, I've got a case called B4 gen ROU sat IEEET1. And so if you open that up, if you right-click, this is a simple case that we use to explain transient stability mostly to undergrads. It's got an infinite bus here. It's got a generator that we're going to play around with the models that we use on that generator. If you right-click on the generator and look at the generator information dialog, and then look at stability, you'll see I've got a gen ROU for a machine model here. Then if you tab one over to the exciter, there's the exciter. I've got an IEEET1 model in here with a bunch of parameters there. One thing PowerWorld does is it lets you know when there's a default parameter value. Whenever we define a model in our code, we set default values for that model. And if the value being used is the default value, we show it in bold.
No, it's default, it's not.
Oh, is that the way?
Yeah,
Really? Those are all default?
yeah, which makes
Oh,
sense.
okay,
You just
the other
put
way.
it in
Yeah.
and change two parameters.
Yeah, okay.
Basically
other way.
there, so if you see a model and nothing is bold, then you know that whoever gave you the data gave you bad data, there's nothing bold.
Yeah, okay, the other way around, yeah.
Yes.
Yeah, the thing to remember about the default values is there's nothing magical about them. We just are trying to pick some values that we think will give a reasonable response. But there's nothing magical about them. You know, in setting up this machine, somebody set those values in that exciter. And they set them for a purpose. Okay, so if we go to add on transient stability,
Where's the inputs for the under and over excitation limiters in that?
the good thing about an IEEET1 is that was before under and over excitation limiters, so those don't exist.
Yeah, some models don't have.
Yeah, some models don't have them. And
So this is one that will let it just go really high. There's nothing gonna limit it.
yeah, it's just whatever the block diagram shows. So the VR is gonna provide some limitation on it, but the saturation function is gonna provide some limitation as well. The good thing about, you know, simulations and little simulations is you can abuse them however you want. Change parameters around and see what they do. So in this case, I've got a fault at bus 3. Bus 3 is this bus in the middle here, and I get rid of the fault by opening the two lines into bus 3. So if we do run transient stability, I've got it set to show a graph of the field voltage. So if you just go ahead and click the run transient stability button, you should see something that looks like that. Okay, and that's just how the field voltage changes going into the generator. Okay, and again, I'm applying the fault at time t equals 0. T equals 1, so it's flat until 1. Then you get, during the fault, the field voltage is going up, then it oscillates around and it steadies out. Okay. And you might say, well, what would happen if I changed the gain on this? Maybe I don't like that response. So let's go and change the gain on it to, say, 500. And so I go back here to stability, exciter. I'm going to change the gain from 50 to 500. And let's say we don't want to have any limits. so I'm gonna set VR max to be 99 and VR min to be minus 99. Okay, and then do run transient stability, and now you get that response. And you say, is that a better response or is that a worse response?
Oh, excuse me.
It looks unstable to me. It's like it's growing at the end. So I would
Yeah,
say
so
worse.
you might look and you say, I wonder what goes on after time t equals 10. So because this is a four-bus system, let's run it out for time t equals 60. And then you run it out for 60 seconds, and lo and behold, that thing's oscillating. Okay, it's just oscillating. And this system is helped, it helps to keep it under control by having an infinite bus there. Because that infinite bus, no matter what you do to that infinite bus, it's not changing. So it prevents this generator from causing too much mischief. Okay. So this one's oscillating. The nice thing about a high gain is you get a quick response. Okay, it's just like if you're driving your car and you want to, turn really fast. If you turn fast, you've got high gain. Okay, that might not be a good thing to do, but you respond quickly. Or you want to you want to accelerate from say 60 to 70, and you just slam down the accelerator, you'll accelerate fast. But you might get some overshoot on it, and you might go unstable. Okay. But
Then I wouldn't go unstable going from 60 to 70.
Not a Ferrari, not really.
yeah, okay. 75, okay.
Yeah, not on the street.
Red Ferrari, right, Jim?
It is.
So, can we handle that gain of 500? I'm on slide 38. Well, let's change it. Keep the gain of 500, keep the VR limit, and let's put some feedback in there. So set the KF value to 0.05 and the TF value to 0.5. 0.05, 0.5.
That is it.
So now we've got the high gain, but we also stabilize our response. Okay, so whether you want that sort of high gain, and whether, we took off our limits on our VR, so maybe it can't really do that. The field voltage is going rather high to do this, but we do get quick response now. So we've got a high gain, we've stabilized it, and maybe it's what we want, maybe it's not. Okay. So the gist on the machine is somebody set the parameters that define the response of that exciter. Okay, and they set them for a reason. And you're balancing when you do a control system. We'll talk about control system design in a little bit, but you're looking at how fast you respond, how much overshoot is allowable, how much steady state error do you have, things like that. That all goes into control system design, which is ultimately what we're doing on these generators here. Okay, I just looked at, okay, so we did that. I showed you how to view the model parameters. In a 2019 WCC case with 3,510 active exciters, 19 were modeled with an IEEE T1, which is old, 179 with the EXSTI, and 22 with the ESDC1A. So about 5% are represented with some variation of an IEEE T1. This shows the KE values for the EXDC1 exciters. About 2/3 have a KE of 0, and about 1/3 have a KE of 1. Other DC exciters exist, such as the EXDC2, which is quite similar to the EXDC1. It's sort of like saying, what's the difference? No, it's not much different, but it's going to respond differently during a fault because the limits here are multiplied by the terminal voltage. So during a fault, when your terminal voltage is low, it locks down your limits. So your limits go down during the fault. So this might not seem like a lot, but if VT is small, then it's going to limit its behavior during the fault. Okay, so that's the only difference with the EXDC2. There's a ESDC4B. This is a newer model introduced in IEEE 421.5 in 2005, in which a PID controller is added. That could represent a retrofit on an exciter. So this is pretty much as before. There's the amplifier, there's the feedback. But now, rather than having that lead lag, we add in a PID controller. And if you're not familiar with PID controllers, when we get to governors, we will talk about how you design the parameters for a PID controller. PID controller is a very common control design where you combine a proportional response with an integral response with a derivative response. And we'll talk about that a little bit later on when we get to governors. Okay, what do you want for performance from an exciter? So a discussion of the desired performance of exciters is actually contained in IEEE standard 421.2, which was updated in 2014. You might look at either large signal performance or small signal performance. In large signal performance, you've got an often discrete change in the voltage due to a fault. You might have significant nonlinearities, and limits can play a role. In small signal performance, you've got small disturbances in which you've got close to linear behavior can be assumed in your device. And increasingly, exciters have input from power system stabilizers, so performance with these signals is important too. And when we get to stabilizers, I think tomorrow, we'll talk about how the stabilizer and the exciter characteristics couple together in the design. But you might look and say, okay, what sort of transient behavior do I want out of my device? And anytime you have a transient response, you're at some value. You take your Ferrari from 60 to, how fast?
75.
No, you're only going to 75. Okay, so you're going
are
at
we
60.
on the road?
Yeah. And you want to go to 75. How do you want to get there? This
Safely?
is, well, yeah, this is a plot of your speed versus time. And you want to go from 60 to 75. And, it's like, how fast do you want to do it? What's your rise time? Going from 10% of the difference to 90% of the difference. How much overshoot do you want? Do you want to get up there by going to 80 and then settling back down to 75? So what sort of overshoot do you want? What's your settling time before you settle in? Are you going to oscillate around or not? That's all something that goes into control system design. And that would affect your large signal performance. In small signal performance, we're going to be looking and saying, what sort of gain do we have on the system, and what sort of phase lag do we have on the system, and that ties into the small signal response. It can be assessed either by time responses, a frequency response, or an eigenvalue analysis. This shows a typical open loop performance of an exciter in a machine in the frequency domain. Tomorrow, when we talk about the stabilizer design, maybe it's Thursday, we'll show how you can put a signal in and test to see what sort of response you get out of your system. Okay. Any questions on the DC exciters? AC exciters, almost all new exciters use an AC source with associated rectifier, either from a machine or a static one. AC exciters use an AC generator and either produce a stationary or rotating rectifiers to produce the field. That's an example of an AC exciter. The difference here is we've got an AC machine for the exciter. With an AC machine, you have to, of course, rectify it, because ultimately what we want is a DC field current to go into our synchronous machine. We're again sensing some values and feeding them back. In the 1968 paper, they represented an AC machine using an IEEET1 there. That doesn't look a lot different from an IEEET1. We've got pretty much the same sort of model here, which would represent an AC machine. We've got our voltage amplifier there. We've got our feedback. The only difference is the feedback includes an additional term on it. But other than that, that's the IEEET1, but it's representing an AC machine. By the time we got to 1981, they had changed this one substantially, and the substantial change was this functionality in here. The FEX function represents the rectifier regulation, which results in a decrease in the output voltage as the field current is increased. So this is representing the rectifier behavior on the machine. Okay, you should see some things that are similar here. Lead lag block there, there's the voltage amplifier, and there's a feedback there. About 3% of the WECC exciters are EXSTI or ESAC1A. This function here that appears right in there, that's actually implementing a curve that looks like that. The details of it are not particularly important for you guys. When we simulate this, we look and say, are we on one mode, another mode, or a third mode of the curve? The curve's represented in the software using three segments that are defined in the standard, so the function that we're implementing just comes right out of there. The KC represents the commutating reactance on the machine. Okay, static exciters. In a static exciter, the field current is supplied from a three-phase source that is rectified, so there's no separate machine. The rectifier can be either controlled or uncontrolled. Current is supplied through the slip rings. Just on a static exciter, you can get very fast response. So that's an EXSTI1 block diagram. You might notice something has vanished. Yeah, none of that machine junk. That's all gone. I mean, it's saying it's so fast we just get rid of it. We just pretty much represent it with limits here. It's so fast you're not worrying about it. So you've got just parameters that you're sort of setting. There's the voltage gain, the TA value on your amplifier, the lead lag there, the feedback circuit. That gives you a very fast and controllable device. So you just have to say, okay, is this fast control something I want? But it's something that is out there now, and then you can design it to say how fast you want it to be. It's the most common exciter in the WCC, with about 15% modeled with this type. KC represents the commutating reactance in it. So the exciter time constants are assumed to be so small that they're not represented. There's another common one, the EXSTI-4B. They're a controlled rectifier design. Field voltage loop is used to make the output independent of the supply voltage. So it's a very designed system where you can kind of almost represent whatever you want with this in terms of the response of the device. But they're very fast responding devices. Okay, so that covers exciters. Is there any questions on exciters? Have more detail than you wanted to know about exciters? Compensation. Oftentimes it's useful to use a compensated voltage magnitude as the input to the exciter. When you bring a signal into the exciter, it does not have to be the terminal voltage. It's commonly a compensated value. Usually it's just compensated with the XC value here. RC is usually 0. One of the confusing aspects here is compensation. There's a sign convention here. The IEEE 421.5 standard is like that. PSLF and Power World have a minus sign there.
Yeah, all the software vendors do not follow the standard.
Yeah, all the software vendors don't follow
I don't know why the standard.
Uh-huh.
Yeah, Tom, so why would you want to do this compensation, not use the terminal voltage directly?
Right there, the idea of compensation is you're trying to look at a different signal to either allow multiple exciters, or to have multiple generators in parallel. You can either compensate so you're looking inside of the machine, or you can add compensation so it looks like you're controlling a voltage partially through the step-up transformer. A reference on this came from your guy Carson Taylor in 2000 in the summer meeting. That was when we were all interested in voltage stability. During the voltage stability days, the idea is that we could get better voltage stability in our system if we compensated to a point partially through the step-up transformer. But you can also compensate through the machine, so it looks like you're regulating a voltage inside your machine. Then it's easier to parallel generate, put generators in parallel.
So all your hydro.
This is the WECC. I think I looked at the Gen RU models. Overall, about 30% of the models use compensation. And almost all of that is compensation inside the machine, not looking on the high side.
I suspect there's more of it in real life. But I don't know when you guys do. That is about okay.
That's about right.
People
I mean,
don't
that's
regulate
what it
it.
is. I didn't break it down by BPA, but, yeah, so compensation is certainly out there. It's not used all over the place. In the interest of getting out of here by 4:30, we won't go through the examples, but I've got different examples here that talk about compensation. That's one example there. One of the key things you have to think about in stability is initial limit violations. Many of the models have limits, and the initial state variables are dependent upon what it did in the power flow. What was the power flow state used to initialize the transient stability? Of course, most of the time those limits are not violated in transient stability. Most of the time everything's fine for most of them. But when you solve software, you can't talk about most. You have to deal with everything. And the issue is, what do you do if the input from the power flow violates a limit? What do we do? And there's three options in Power World for dealing with this. One is you can just abort and say to the user, it's your problem, fix it. Most users don't like that option. So it's not our default. The other one is to say, well, you know, we'll just violate the limit, and when you violate the limit in the dynamics, it's gonna go to some other state. So you're gonna have a system that does not initialize flat. It doesn't initialize at an equilibrium point because you told it an initial condition that is in violation. So it's not at an equilibrium point, so it'll go somewhere. We don't know where, but it'll go somewhere. The third one is to say, we'll just change the limit. And we don't permanently change the limit. We just temporarily change the limit in your stability study. And that is right here on the Power World Transient Stability under Options. It's under Power System Model Options, Handling of Initial Limit Violations. The default is Modify Limits and Run. Okay. So, just so you know that.
Is there a way to get a printout of where it wants to initialize at versus where the initially is coming in from the power flow?
We log all these changes.
The change is logged, but do you also have a way to compare what the limit is coming from the power flow and where it's predicted to be with the initial state of the stability run?
Basically, would there be a way to feed back and say, okay, your bar limits need to be in here, otherwise you're excited outside?
No, we don't do that. That would be hard to do.
Could you just do a run with no event, you know, just see where it settles out? And
Oh, yeah.
And then
yeah, that's fine.
just
Yeah.
compare all the state variables with what it was initialized at?
Yeah, that.
Yeah, you can definitely do that. Governors are used to control the speed on your system. This is kind of a cartoon view on a governor, which I got off of Wikipedia. Of course, a synchronous machine is used to convert mechanical energy from a rotating shaft into electrical. The prime mover converts it. You can have different sources for that, of course, steam, hydro, gas. The governor is used to control the speed. And this is an early governor. It's a flyball governor where it's a simple control device where you want your generator to move at some speed, and you have a flyball where the balls go up if it's going fast, they come down if it's going slow, and you use that to control a valve position on your machine. Of course, we've come a ways since then. So collectively, the prime mover and the governor are called the governor. So the governor is, what we call the governor includes the physical control system and the turbine models as well. So they're integrated together. In transient stability, the response to the system for seconds to perhaps minutes is considered. So usually the governors will not bring the system speed back to steady state of 60 hertz. That's controlled by the longer term automatic generation control. Okay, let me just show you a movie of the response of a system, the WCC, following the loss of the double Palo Verde fault. This is in the Talk 4 directory, so it's the WECC _15 second, 1/3 real-time playback. this is a contour showing the frequency across the WCC for outage of the double Palo Verde plant in Arizona. And this is showing with the contour how the frequency variation goes across the system. We're running at 1/3 real time here. Blue is 60 hertz, kind of this magenta is 59.7. And you can see how it oscillates around in the system. Okay, this was a movie that we made up back in the olden days when we couldn't do this automatically. We've since made it a lot more easier to create movies like this. But this one I made by going through a transient stability run and pausing it every 0.05 seconds and storing the image as a JPEG and then using a movie maker to put them together. That got automated. So it's much easier to do now. Okay, so that just explains how the system would respond to a loss of generation. If you're interested in some references on governors, Kundar's book is good, Wollenberg and Shebley is a good book. This is a paper that was put out on the dynamic models, and then there's some earlier models that were standardizing the governors that were used in transient stability. This is an Eastern interconnect plot showing how the frequency in the system is varying normally over the course of, this is an hour long, so each one of these is 10 minutes. There's a loss of generation. In this case, it's a loss of two 1,300 megawatt generators. Initially, the system frequency is falling as the stored energy in the rotors is converted into electrical energy, and then the governors start to respond. They bring the system back to a certain point, and then the AGC brings it back to 60 hertz on a longer time scale. The transient stability studies would be looking at this period in here. Interesting metric that is used on systems by FERC is to define the frequency response of the system. FERC defines this in RM 13-1. The frequency response is a measure of an interconnect's ability to stabilize frequency immediately following the sudden loss of generation or load, and is a critical component to reliable operation of the bulk system. The design event for WCC is, I think, Palo Verde. Is that still true? Double Palo Verde fault. And it should not result in under-frequency load shedding at 59.5 hertz. There's different metrics for frequency response. You're operating at some point here before a fault occurs. Then when the fault occurs, you go down to this point C, and then you recover to point B there. And the NERC metrics look at the difference between A and B. You could also look at the difference between A and C. This is a graph. Yeah.
For bonus points, so we win, is BAL003. It looks like that requires stability runs to verify. Would that be ahead of SIC? Or is this just measurement?
I think this is measurement. I'm not sure, but
Right.
certainly if you're running runs, that could help.
Negative bonus points.
Negative bonus.
He said it could help.
This is with your car slowing down now. It's going from 75 down to some slower speed. You don't want to go under too much there.
Lost the cylinder.
Yeah, lost a cylinder. That's a graph showing the frequency response in the WCC, where the blue values are the point C, and the red values are the point, the A to B values. The gist here is how many megawatts does it take of loss to get a 0.1 hertz change? Okay. So the higher the value, if it takes more megawatts of loss to get a 0.1 change, that's a good thing. NERC conveniently provides graphs showing the response here. Okay, so I grabbed this, this might be a little bit out of date, but this is showing the WECC, and they're measuring this from actual events. And the trend line is up, at least it was on the values that I'm showing here. And you can go out and grab that off of the NERC site at that website there. Why are those green dots varying? Why are some dots high and some dots low?
Higher or lower load on the system.
Yeah, load or really more generators online.
What
So-
the event was?
What?
What the event was?
Yeah, I mean, it depends on the event, but this is normalized by megawatts per 0.1 hertz. So it's normalized for the different events. So you can compare the different events because of that normalization. So you're comparing apples to apples here. But yeah, there's going to be some up and down because if you don't have a lot of generation online, you don't have a lot of generators that can respond. So the overall trend in the WECC is positive. There's the Eastern Interconnect where their value is higher in general than your value. So your value is going up towards 2,000. Their value is above 2,000. I guess it's a little hard to tell, but there's 2,000, 3,000 there. And they were on a bit of a downward slope there. ERCOT being smaller is going to have a lower value. So ERCOT, the value here is 500, 1,000. So ERCOT's smaller, so they're lower, which means for a given outage, of course, ERCOT's going to drop down more because there's less generators to respond. Okay, so in looking at the block diagram for controlling generation, the goal is to maintain constant frequency with changing load. If you just had a single generator, then you could implement what's known as an isochronous generator. An isochronous generator is one where you're going to integrate the frequency error and drive it to zero. So anytime in a control system you're integrating something, you're going to drive its ultimate error to zero. Isochronous means ISO is same and Chronos is time. So that drives the system frequency back to 60 hertz. And if you had a single backup generator, that would be a good thing to do. And if you want to look at a simulation of a little system with an isochronous governor, just open up the case WSCC 9bus_ISO-gov, which is in the directory there. And then run transient stability. The event in this one is the loss of the generation at bus 3. And if I run transient stability, it shows a number of different plots here. The one I want to look at is the generator speed. Here, the generator speed, this is the one that opens up. Generator speed dips down and then it recovers back to the final speed. That's set up because I've got an isochronous governor model. An isochronous governor we just added for educational use. You're not going to run the WSCC with an isochronous governor because that governor is going to integrate the frequency error and it's going to try its hardest to drive the frequency error to zero. You don't want that in an interconnected grid. Okay, so we wouldn't have that. you know, in a large system, you can't have one generator doing it all. And that's what an asynchronous governor would try to do. So rather what we do is we use the droop control on the system. And in droop control, the idea of it is that the set point on the governor is frequency dependent. So the governor has a power set point. With droop control, that power set point varies with frequency. So if you look at your power set point, which would be on the x-axis here, you implement it by having a droop or a line that's sloping down, where the slope of the line, the R value, is known as the regulation constant or the droop. And a typical value for the droop is going to be 4 or 5%. At 60% and a 5% droop, each 0.1 hertz change would result in a change in the output of that unit by 3.33%. So the idea of a droop control is as the frequency goes down, we're automatically changing the set point on the generator to try to compensate for that and bring the frequency back up. Okay, and a common value is 5%. Okay, so this just goes through a little example on that 9-bus system saying after you lose a generator with a particular droop, what sort of steady state frequency error would you expect? So if you're looking for an example on that. If you want to do a quick calculation on a whole interconnect, if all the generators have the same R value, then you can use this simple calculation, which basically says the change in the frequency that you get in steady state is the R value times the amount of generation loss divided by the sum of the ratings for all the online generators that are participating in control. And the caveat that they're participating in control is important because if the generator is already at its maximum output, then it can't participate in the control. It's got nothing else to give. This shows an example of a 37-bus case where I've now implemented it with a governor, which I'll talk about in a second, a TGov1 model, showing how the frequency responds. This is a 20-second time study. You're starting at 60 hertz, you drop down, you come up, and then you reach a steady state value. This value here is the frequency error, and that depends upon the droop value that you set. This little graph shows the impact of inertia on a system. The worst case here is a system where you've got low inertia and slow governors. Following a disturbance, if you've got low inertia and slow governors, you're going to get the worst drop in frequency. I mean, I think that makes sense to everybody. The best response is going to be a system that's got high inertia and fast governors. Okay. ACE, of course, is used to restore the frequency to 60 hertz. Okay, a simple model for a steam governor, that's about as simple a governor model as you can get. It's the TGov1 model. The output here is the mechanical power. That's what we're controlling. That goes into the swing equation that Jamie was talking about, that the machine is used with the machine model. The input here is there's a reference point, where do you want the device to be at, and then there's a speed deviation. So it's sensing the speed deviation that's coming in as a negative off of the reference point. Here's our droop constant. This is representing the steam valves on the governor. You've got a maximum valve point, a minimum valve point, some delay there. This is a lead lag that represents things like reheating on the governor. And and then you've got the output here. This would be a case where initial limit violations could cause problems.
That's the most common example.
Yeah, I mean, it's the most common example, because if your generator is putting out more power in the power flow than the Vmax value, or less power in the power flow than the Vmin value, you're gonna have a problem. And the question is, what do you want us to do? Okay, we can't change the power flow output. That's what you do. Okay, so the idea here is if your power flow is valid, then those Vmax or Vmin, one of them's wrong. That's an IEEE G1 model. This is a common steam turbine model. It was originally introduced in the 1973 paper that I give below there. It is used to represent cross-compound units with high and low steam pressure values there. It's a bit of a pain because it's got, you know, two inputs coming into it, so two different machines. So it's potentially controlling two different machines. Okay, but this is just modeling the high and low pressure systems in the steam turbine. The idea here is the K1, K3, K5, K7 should sum to 1, and the K2, K4, K6, K8 values should sum to 1 if they're being used. We have had situations where somebody inputs a value of K1 being like 20, and that causes problems.
Simulator normalizes.
Yeah, I mean, these are all things that we try to fix as much as we can.
But ideally, you're given good data.
Right, when you fix things, it's you don't know that there's a problem. For a while, there was a governor that had a negative R value, which was causing problems. But that's been fixed, I believe.
Yeah, people always, that error is because I know it has to have negative through, but there's always a minus sign on the block factor. Take care of that.
Here, this one uses a K value, like a gain value. K is just 1 over R. Here we've got rate limits in there. How fast can you open the valve? How fast can you close the valve? So those would be rate limits on the device. Yeah, so there's that's a paper that I got out of or those are figures I got out of the paper, Dynamic Model of Turbine Governors of Power System Studies in January 2013. The gist is that sometimes these models fit the behavior of the generator quite well, and sometimes they don't fit the behavior well at all. So this is saying here's a unit where this model, the IEEE G1, matches well, and here's a unit where it did not match well. Okay, about 8% of the WCC governors are G1s, IEEE G1s. Okay, dead bands. Before going further, it's helpful to consider dead bands. Dead bands come into play in a lot of power system responses, particularly on governors. There's two main types of dead bands, and they're described in the IEEE 2013 or the PES governor report. The type 1 is an intentional dead band and is implemented to prevent excessive response. So with this sort of dead band, when you initialize, you're usually in the middle of the dead band there. Okay, the idea is that if you stay within this range, there's no response. So maybe the input is frequency, and the frequency's bouncing around a little bit. As long as it bounces within some range, you don't want to do anything. That's just normal jitter on the system. Once it gets past that point, you respond as though you had been responding all along. So then you go up to this point, and then when you back off, you go down that dotted line. So that's a deadband response. Type 2 is also an intentional deadband, again, implemented to prevent excessive response, but here, as long as you're within the range, you again stay at 0, but once you go outside, then you just start to respond. So it's a little bit different sort of response. There's another type of deadband that is an unintentional deadband, and this has more of a hysteretic response. It would model something like loose gears. So if you had a system where you've got loose gears, the idea on a loose gear is as long as you're not engaging the two gears, you're just jiggling around, you don't have any response. Once you start moving though, you engage, and then if you were to come back, you won't come back to where you started. You come back to a different position, and then if you go the other way, you come back here. So it's got a hysteretic response in it. So you don't reset. One of the issues we're struggling with in the simulations is it's okay if you do a short-term simulation with deadbands where you don't have to get back to where you started. But if you've got a deadband like that and it's engaged, and then the event dies out, you kind of want to drift back to that point and treat it as a new steady state. Okay, we need to figure out how to do that. Okay, I'll skip the frequency deadbands in ERCOT. The next bunch of slides go through various types of governors that you would run into. There's gas turbine governors. This is a block diagram for a gas turbine governor. This is a simple implementation of a gas turbine governor. Quite detailed gas turbine models exist. Some of them are very detailed. One of the things that I'll talk about right now is the idea of having a play-in model. Often in system simulations, we'd like to test a particular response, and it helps if you can set it up so you can play in a particular response. PowerWorld allows you to use either files where you can play in maybe recorded data and modify your system as though you had recorded data in it. We also have a model type called the infinite bus signal gen model that lets us auto-generate a signal. And when you auto-generate a signal, that can be quite useful in testing your system response. So what we'll do here is
Tom uses it to like intentionally play in an oscillation.
yeah, I'll show you that in just a second. This is how we play in an oscillation, and I'll show you that in just a second. This is a governor for a simple diesel model. Not too many diesel models out there, so we won't dwell on it. But one point of this is sometimes in a block diagram you run into a delay function. A delay function is just saying whatever you have here, you delay it and output it. Okay, and the way we, these come up in other governors as well, but the way we implement that is to use what's known as a Pate filter approximation, where you take a delay function, which is just saying the input, or the output is the input delayed by X seconds, and we use a differential equation to implement it. Not too important for the average user, but it's good to know that it's there. And this is an example where we tested it out, where the transient stability input is in the red, and then the green is the output, which is just a delayed input.
It depends how large the delays are short.
do what?
If the delays are on the order of, say, 10 cycles or less, then we'll just keep track of the signal and play it back with the computer.
You sure about that?
I'm sure. There are very few places we found one. I think there are two.
Yeah,
One.
okay.
If you have a really long delay, we can't keep track of that, so otherwise we keep track of hundreds of time delays.
Yeah, I mean, the filter delays aren't too bad. Okay, we're coming in, we'll be done before 30, one way or the other. You know, something of importance to you guys are hydro units. Hydro units tend to respond slower than steam and gas units. There's different ways to represent hydro units. There's the older ways, which are the IEEE G1 and or G2 and G3 models. They just gave a linear response. This is an IEEE G2 model here, and I'll talk about in the next couple minutes the details on where these things come from. But before I do that, let's do an example where we do a signal generation here. So open up the case B4 signal gen IEEE G2. And in this, it's that same 4-bus system. If you go to bus 4 and right click on it and look at the generator information dialog and then go to the stability tab, we've got a gen ROU, we've got an exciter there. I used an EXSTI exciter, which is a very common exciter. It's a static exciter, it's very fast. And then for the governor, I've got an IEEE G2 governor in here. Okay, and let's say you want to test the response of your system somehow. So if you go to the other side, the signal gen, you right click on that and look at its generator information dialog and go over to the stability tab. There's no governor, there's no exciter, but rather under machine model, there is something called an infinite bus signal generation. And what this does is it's an infinite bus, but it can have a varying voltage magnitude and frequency. And we use these to shake systems. So what it does is you can either, for your changes on it, you can either ramp them up or not. We're not going to ramp anything because we just want to look at a sinusoidal variation. It implements a number of piecewise, not linear, but piecewise time segments of response. And it's saying, when do you start it shaking, or when do you start it changing? I just set it to 1. How much do you want me to change the voltage magnitude of this signal generator by? And at what frequency? So we're going to leave that equal to 0. And then you say, how much do you want me to change the frequency at? How much change in frequency? Let's say it's 1 hertz. And at what speed? And here I've got it set up so the change here is no hertz. So it's just going to drop it down to 59 hertz. So suddenly this infinite bus is at 60 hertz. It goes down to 59 hertz. And that goes on for 4 seconds. And then the next segment starts, and the next segment ups it by 1 hertz, so it goes back to 60 hertz. So what we're going to get out of our signal generator is its speed is going to be at 60 hertz. It's going to drop down to 59 hertz. Then after 4 seconds, it's going to go back up to 60 hertz. And the only reason I'm doing this is to test my governor's response. So at that other bus, we've got the governor. The governor is going to, of course, if the frequency goes down, it's going to try to increase its output. Okay, but being a hydro governor, when the frequency goes down, initially its power output drops, then it comes back up. And here you can see some oscillation in there, and then when I change it around, it does the exact same thing. So if you go ahead and run that,
I've never had a solid handle on why hydro governors do that. I know they do, but why?
Jay might talk about that.
I know, I always forget.
All right, well, you'll get it soon. Yeah, it's because of when you open up a valve, you're not changing the speed of the water instantaneously, but you're dropping the pressure. Okay, because the water has inertia, but that's coming up. Jimmy's getting it up. So anyways, that's the response that you should get there. Okay, so we use these all the time. Sometimes it's kind of fun to take a system and put an infinite bus on it and put like a 1 hertz signal out into it and just like shake the system and see how it responds. You can get a good feel for what your models are doing. One of the problems we have with models is you can have underlying things like errors and limits that you don't see unless those limits become active. And in normal operation, those limits aren't going to become active. So they can persist for a long time because if nobody stresses them, or even if you stress them and you don't notice that something didn't respond as expected, you won't see it. But if you really shake the system, sometimes you see all sorts of interesting stuff. Okay, so going forward, a common filter that's used in stabilizers and also appears in governor models is called a washout filter. A washout filter is a high-pass filter that removes steady-state response. This is the block diagram for a washout filter where you have a TW value in the numerator, that top one, and in the denominator. If you look at a washout filter, the way, if you're not familiar with block diagrams and filters, the way to think of its response is when S is 0, DC, the top one, the numerator, is 0, the bottom one's 1, so it's blocking it, it's not passing it through. And then as we go to higher and higher frequencies, the numerator and the denominator become equal, so its gain is equal to 1. So it's a high-pass filter. It's passing the high-frequency stuff, and it's attenuating the low-frequency stuff. And this is commonly used in stabilizer design where you don't want to respond to the steady-state changes in the system. You just want to respond to the disturbances. So you'll commonly see washout filters. They're also commonly used with hydro governors here. And when you look at a hydro governor, we'll see washout filters appearing here. There's one right there. And this is the IEEE G3 model. This was a very common WCC model. About 10% of the governors were previously modeled with this. When I checked in 2009, it's 5%. So this one's going away. It's an older linearized model, so it's a good thing that it's going away. But it gave an okay performance for a hydro unit. And on a hydro unit, you have your droop here, the R value, but you don't just have a 1 R value, you actually have 2 R values. There's what's called the R perm value and there's a R temp value. The R temp value is typically much larger than the R perm value, so it gives you a temporary R value that is much higher than the other R value. And the way you do that is you couple that with a washout filter. So if a high frequency disturbance comes in, this one here essentially passes R temp. So you've got R perm in parallel with R temp, and you're seeing that higher R temp value. When the high frequency disturbance goes away, this goes to 0, and you just get your permanent response on it. So it gives you a transient response that results in less power change transiently on your machine. You might say, well, who sets these values anyways? And you can actually find equations for tuning these values. Kundar has in his book the equations that you use to tune these values. They're based on, they're based on the water constant, which comes off of your turbine governor, and they're based on a TM value, which is called the mechanical starting time, that depends upon the inertia of the machine. So here you would tune this based on the characteristics of your machine. And what I did is I went through a WECC case and I looked to see what are these values actually set to, and surprisingly they're set to values that are very close to what you get out of these equations. So somebody went through and, you know, I mean, obviously you've got this hydro unit, somebody is, you know, setting the parameters on the governor response. And what they're setting is pretty close to what's given by these equations here. So, Jamie, what do you want to do? Just pick this up tomorrow?
Yeah, we can just pick it up in the morning.
Yeah, we're about 20 slides from the end, so just take maybe 15 more minutes. But if you're interested in seeing how an IEEE-G3 responds, B4 signal gen underscore IEEE-G3 shows the response here, and it compares different values of R temp versus R perm, and you can see how they compare on their response.